Welcome to video 41 in our series on tensor calculus. In this video, we'll analyze the motion of a particle as it sweeps out a path in space. Consider a small particle moving through space as a function of time. Now we call the path that such a particle traces out a trajectory. To analyze a trajectory, we're going to make use of our old friend, the position vector. Only this time we're going to represent it as a function of time. Now, of course, if we're going to use a coordinate system, which we are, then we also need to represent our position vector as a function of our coordinate system z. And because of the time dependency, z is a function of time. So we can create this composite function. And of course, that lets us use the chain rule when analyzing it. All right, well, first of all, our position is represented by the position vector r, but we now want to ask the question, what does it mean to talk about the velocity of our particle? Well, the velocity is defined, we'll use a vector v here, our velocity is defined as the time derivative of the position vector, so it's just dr dt. Okay, but because of the composite relationship here, we can use the chain rule to expand this out. So first we'll take the partial derivative of r with respect to zi, and then the ordinary derivative of zi with respect to time. So it looks just like this. Okay, now just as a brief review here, remember that our position vector r is a function of z1, z2, z3. So our position vector is a multivariable function, and that's why we have to use the partial derivative here. But where zi is concerned, it's simply a function of the single variable t, and that's why we use the ordinary derivative here. Okay, well, the partial of r with respect to zi is, of course, the definition for our covariant basis vector. So we can rewrite the expression this way. We'll switch the order of the terms, dzi dt, and then the partial here is just our covariant basis vector, zi. All right, well, what we've got here then is a linear combination. We've got a vector on this side, and we've got a product of a scalar factor times the basis vector here. This dummy index here is going to create three terms. So we have three terms of a scalar times a vector, etc. Now, we also know from the quotient theorem that since this is a vector, any derivative of any vector is a vector, and we know the basis vector is a vector, so that means that our scalar factor here is a tensor, and we get that from the quotient theorem, of course. All right, that means that we can represent our velocity vector then as a linear combination this way. We have v, which is equal to some contravariant vector component vi times our basis vector zi, where the scalar factor vi is defined as the time derivative of our coordinate. dzi dt is the definition for the contravariant vector component of the velocity vector, and that lets us use this form as a linear combination for the velocity. Now, before we move on, let me point out something that's very important. Here we expanded our definition for the velocity vector using the chain rule this way. Well, we can also expand it out using the chain rule with respect to the arc length of the curve. In other words, we could say that our velocity vector is equal to ds dt, this is the arc length of our curve, times dr ds. This is just the ordinary chain rule involving a single variable s. Well, in video number 8, we discovered that dr ds is just the unit tangent vector to the curve. It's equal to s hat. So this would be equal to ds dt times s hat. Now what that tells us is that our velocity vector, as we've defined it here, is going to point in a direction that is tangent to the curve, and its magnitude is going to be equal to this factor right here. So this is what we can say, that our velocity vector is tangent to the curve at each point, and its magnitude is equal to ds dt. All right, well, let's move on now and talk about the particle's acceleration. Well, just like the velocity is defined as the time derivative of the position vector, acceleration is defined as the time derivative of velocity. In other words, our acceleration vector A is going to be equal to dv dt. Okay, now, just like r up here, our position vector is a function of time and also a function of position and time. The same can be said about our velocity vector v. It's a function of t. It's also a function of z and t. So we can use the same chain rule expansion here that we did for velocity. We can say that this is equal to the partial derivative of vector v with respect to z, and I'll use a different index this time. I'll use zj times dzj dt. Okay, well, here the partial of r with respect to zi was our basis vector zi, but we're going to get something different with the partial of v with respect to zj. Now, to understand what that is, we need to go all the way back to video number 28. If you remember in video number 28, that's where we introduced the covariant derivative. And to do that, we were in the process of finding the partial derivative of a vector t with respect to coordinate zj. And if you remember how that worked out, we expressed our vector t as a linear combination. Then we used the product rule to expand it out, and we then introduced the Christoffel symbol, and combining that with the first term, renaming some indexes, we wound up defining the covariant derivative. So this relationship turned out to be the covariant derivative of our vector component ti times our basis vector zi, like this. Okay, so that's what we did back in video number 28. Now, we could do the same thing here, but we don't need to because we've already done that. All we have to do is to replace t with v in this expression, and we can expand it out that way. So that's what we're going to do. We're going to say, first of all, that we'll reverse the order of the terms. We'll have dzj dt, and then this first term right here, we're going to expand out in this form. We're going to have the covariant derivative with respect to j of vi times the covariant basis vector zi. Now, the end result of all this is once again a linear combination. It has the same structure as velocity. For velocity, we had a linear combination with our basis vectors using this as the scalar factors. Well, acceleration is also a linear combination using our basis vectors, only this time this expression right here represents the scalar factors of our linear combination. Okay, well, at this point, I want to introduce a new definition of something we call the intrinsic derivative. Also known as the absolute derivative or the total derivative. Well, what is this thing? What we've got is the definition of a new type of derivative taken with respect to a parameter lambda that is used to define a curve in space. Now, it can be applied to a tensor of any rank, and that's why I've represented it this way. You can have as many contravariate indexes and or as many covariate indexes as we want, including none. This could apply to a tensor of any rank, including a scalar function with the rank of 0. So to get an idea of what this is, let's do that. Let's apply this to a simple scalar function. We'd have the intrinsic derivative of a scalar function f with respect to lambda. Well, according to our definition, we'll have dzm d lambda as the first term, and the covariant derivative with respect to m of our scalar function. Well, we can break this first term down using the chain rule and the arc length. So this first term would be the same as ds d lambda times dzm with respect to ds. So these two terms together are the same as the first term. And for a scalar function, the covariant derivative of a scalar function is the same as its partial derivative. So this is the partial of f with respect to zm. And finally, we can combine these two factors together as the chain rule to give us simply ds d lambda here as the first term. And these two together would give us df ds. Okay, now look at what these elements are. This guy right here you'll recognize, I hope, as the vector component of the gradient. This concept we developed back in video 39. So this is the vector component of the gradient, and the same is true here. And this term is the set of vector components for our unit tangent vector s hat. And when we combine these two together, what we get is the directional derivative, which is where we started back in video 39 in the first place. We broke the directional derivative down into this product and ultimately into this relationship right here. So when we apply the intrinsic derivative to a scalar function, we basically wind up doing the same thing we did in video 39. We found the directional derivative and broke it down to the gradient and its tangent component of the tangent vector. Well, what this intrinsic derivative does, it sort of generalizes the process to tensors of any rank. And therefore, what this does is it gives us information about how these tensors change as we move along the curve parameterized by our parameter lambda. Well, let me take a minute to talk about a couple of the properties of this new operation. The first one is this. In other derivative operations, almost everything we've done so far in tensor calculus, we've taken a derivative with respect to some indexed object like zi, and the result is that the new index in the lower component here has added a new index to the rank of the expression. So if we started with say a second rank tensor here and took the covariant derivative, the result is going to be a third rank tensor because of the index added here. Well, now we're taking the derivative with respect to a simple variable and not an index object. And what that means is we don't introduce a new index. Therefore, the rank of this tensor is the rank of this tensor, and because this is a dummy index, the rank of the result of this operation is the same as that of the tensor we started with. So the rank does not change as a result of this operation. Now, the other thing I want to point out is that this operation is very closely akin to the covariant derivative, obviously because the covariant derivative is part of the definition. But as such, and because of the linear nature of it, it's very easy to show that it carries most of the properties of the covariant derivative. It will obey the sum rule, it will obey the product rule, and we find that the metronyllic objects are metronyllic with respect to this operation, just like they are for the covariant derivative. Okay, well, we'll say a lot more about the intrinsic derivative in future videos, but right now let's return to the task at hand, and that's to talk about how this relates to the acceleration of the particle moving through space. Well, I think you can see that this operation right here is really the intrinsic derivative. It carries the same model of this. It's just the intrinsic derivative applied to a tensor of rank 1. So that being the case, we can say this about the acceleration. The acceleration vector A can be written as, we've defined it as dv dt, and then it can be broken down into a linear combination of ai times zi, where the vector component ai is equal to the intrinsic derivative of our velocity component vi with respect to time. So this definition lets us write the component of our acceleration in a very simple way. It gives us a great syntax for representing the acceleration of our particle. Now, while this syntax is very simple and elegant, it isn't very useful when it comes to actually finding out the expressions for each of our coordinate systems. So I want to take the time now to expand this expression out into a more usable form. So let's do that. We'll expand it out this way. It's got d zj with respect to time, and we'll expand out the covariant derivative here, which of course is the partial derivative of vi with respect to zj. And being an upper index, we're going to need to add a term with gamma ij and add a dummy index k and vk to complete the covariant derivative. Okay, now we'll distribute these terms out. This one into here will be dz dt, dzj dt, times the partial of vi with respect to zj. And then we'll distribute this in as just a factor. Will be gamma ijk times the derivative of zj with respect to time and vk. All right, well, the fact is these first two factors here, these together are the chain rule that when combined together just give us dv dt. So we can replace this first term with just dvi dt. That's the same as this pair of terms right here. And next, this expression dzj dt, if you look back at our definition for vi up here, this is just the expression for vj. So the second term resolves to this. It's gamma ijk times vj in place of this expression, and then vk. So this is a much better form right here for actually evaluating what the acceleration component looks like in each of our coordinate systems. Now, the real power and strength of using the intrinsic derivative in the context of what we're doing here comes when we continue on with the process to find the next order relationship. So let's do that. Let's define something we call the jolt. Sometimes it's called the surge, represented by the letter J, and we define that as the time derivative of the acceleration. So we just continue on with the same pattern that we had before. And what we want to do is to be able to represent this as a linear combination with some contravariant vector component, ji, and the basis vector, zi, like this. Okay, well, we're in luck because if we're using this definition like this, then if we worked our way through it, we'd go through the same analysis we did up here for the jolt that we did for the acceleration. So we'd do exactly these same steps, except we would apply them to the acceleration. You know, the jolt here would be equal to the time derivative of acceleration, which means that this would get replaced with acceleration. It means that this would get replaced with the acceleration component, but everything else remains exactly the same as we did it for acceleration. In other words, we're led directly to the result that our vector component for the jolt is going to be the intrinsic derivative of the acceleration component with respect to time. We don't need to keep redoing this analysis each time. We just take the next order of the intrinsic derivative. And of course, we could do the same kind of thing here that we did for acceleration. We could come up with another expression for the jolt, but it's going to be much more complicated and not very useful. However, it's also appropriate to say that we could express it this way. Being the first derivative of AI with respect to t, we could say that it's the second order intrinsic derivative of our velocity component with respect to time. So these things act syntax-wise a lot like the simple derivatives with respect to time, except they're generalized and they work for any coordinate system. Okay, well, that's a lot to take in, so let's take a break at this point and go recap what we've done. What we did in this video was to define a new operation known as an intrinsic, absolute, or a total derivative. Now, the operation is a derivative operation taken with respect to a parameter lambda, which is used to define a curve in space. That's an operation that can be applied to tensor of any rank, and that's why we represent it this way. You can have as many contravariant and or covariant indexes as you want, including 0. It can be applied to a simple scalar function. Now, what we have here is a dot product, exemplified by this dummy index right here. So we're really taking a dot product between these components, which are the vector components of a vector that is tangent to the curve defined by our parameter lambda, and this covariant derivative. So in that sense, it's very much like the dot product we saw in video number 39, when we took the dot product of s hat with the gradient. And this new operation performs basically the same sort of function at a general level to give us information about how our tensor is changing along the path that is defined by our parameter lambda. We're in effect taking the covariant derivative of our tensor in the direction of the vector that is tangent to the curve. Now, this new operation has a couple of interesting properties. First of all, the result here has the same rank as the object we're operating on. The rank does not increase as a result of taking the derivative. And also, because it's closely related to the covariant derivative, it has many of the same properties, such as the sum rule, the product rule, and all of the metronomic properties. They're all preserved here. And I might add that we take the intrinsic derivative of a tensor, we will get a tensor on this side as well. Okay, now this is the general form, but when it comes time to actually expand them out and to see what they look like, I'm going to give you several examples here and show you how easy it is to expand this out to a meaningful form when we need to evaluate it. When there are no indexes, the intrinsic derivative of a scalar function is just the same as its derivative. When we add a contravariant index, we start with the simple derivative here, and we add a term for this free index right here. You'll notice this term we're adding is very much like the term we add in the covariant derivative. In fact, it's exactly the same term with the addition of this factor. Likewise, if we have two free indexes, we'll take the derivative and then a separate term for each of the two free indexes, one for I and one for R. And the rules are the same as that of forming a covariant derivative, except we just add this extra factor out front. So it's very easy to expand these out to any rank that we want to use this for. Now, we were able to make use of the intrinsic derivative as we analyzed the trajectory of a particle as it moved through space. And we came up with these results. A very consistent form for each of these expressions. We define the velocity of our particle as the time derivative of the position vector here. We define the acceleration as the time derivative of velocity and the jolt as the time derivative of acceleration. And in each case, we showed that we could represent them as linear combinations. And in the case of the velocity component, it's simply the time derivative of our component zi, but in the case of acceleration and jolt, it's the intrinsic derivative, first of all, of the velocity, then of the acceleration in turn. And this one as well can be represented as the second order intrinsic derivative of velocity. So the pattern continues for as many orders as we want to apply it. Well, we also showed that the acceleration can be expanded out to this form. And if you look at it closely, you'll see that this is very similar to what you see right up here. It's just the evaluation of the intrinsic derivative for a vector component with a single contravariant index. So what we're going to do in the next video is to use this expression and this one to see what the velocity and the acceleration look like for each of our sample coordinate systems.